Today, we're going to tune into the soundtrack of the universe itself. Seriously, we're talking about gravitational waves, these incredible ripples in the very fabric of reality. They were predicted a century ago, but we've only just recently been able to hear them for the first time. So let's lean in and listen to what the cosmos has to say. You know, for over 100 years, a question like this was pure theory, something for minds like Einstein to ponder. But then, on September 14th, 2015, everything changed. We didn't just calculate an answer, we actually heard one. It was this tiny little chirp, lasting less than a second, that had traveled across the universe for over 1 billion years just to reach us. So, scientists gave this signal a name, GW150914. It was picked up by the twin LIGO detectors in the United States. And what they heard, well, it was the echo of one of the most violent events imaginable, coming from an almost unbelievable 1.3 billion light-years away. And this is where the cosmic math gets really wild. You had two black holes, right? One was about 29 times the mass of our sun. The other was 36. They spiral in, they merge, but the final black hole was only 62 solar masses. Now wait a minute. 29 plus 36 is 65. So where did those missing 3 suns worth of mass go? Well, that missing mass was converted instantly into pure energy, a massive blast of gravitational waves. The power released in that moment is it's almost impossible to wrap your head around. For a split second, that one collision outshined every single star in every galaxy we can see, combined by more than 50 times. It was a literal storm in the fabric of spacetime. Okay, so that brings us to the really big question. What are these ripples? To get that, we actually have to jump back to 1916, to Albert Einstein and his groundbreaking theory of general relativity. See, Einstein's big idea was that space and time aren't just an empty backdrop. Instead, they're woven together into this dynamic, four-dimensional fabric he called spacetime. Big things, like planets and stars, bend and warp this fabric, and that curvature is what we feel as gravity. But what happens when those massive objects move? When they accelerate, like two black holes spiraling into a collision? They create ripples in that fabric. Think about dropping a pebble into a perfectly still pond. You see those ripples spread out, right? A gravitational wave is kind of like that, but instead of distorting water, it's distorting space-time itself. As one passes through you, and they do, it would actually stretch and squeeze everything. The room you're in, your body, the atoms you're made of, first in one direction and then the other. And you have to understand, this was a huge shift in thinking from Isaac Newton. For Newton, gravity was this mysterious force that just acted instantly everywhere. If the sun were to suddenly vanish, Newton thought we'd feel it right away. But Einstein said, no, that's not right. The news that the sun is gone, the change in gravity, can only travel at the speed of light, carried by these gravitational waves. So the key thing to remember here is that you need something truly epic to make waves big enough for us to detect. You need absolutely massive objects moving at insane speeds. So what kind of cosmic fireworks are we listening for? Well, the universe gives us some pretty amazing sources. The loudest ones, the heavy metal concerts of the cosmos, are these binary systems. You get two super dense objects like black holes or neutron stars locked in a death spiral. As they get closer, they whip around faster and faster, churning up space-time until a final violent merger. But we can also hear other things, like the chaotic blast of a lopsided supernova, or maybe even the steady hum of a single spinning neutron star, if it's not perfectly round. Predicting these waves was one thing. But actually finding them? That was a century-long quest, a real story of scientific grit against almost impossible odds. So after Einstein's prediction in 1916, decades just rolled by with nothing. But then, in 1974, there was a huge breakthrough. Two astronomers, Holtz and Taylor, found a pair of neutron stars orbiting each other, and they noticed the stars were getting closer, at the exact rate Einstein predicted if they were radiating energy away as gravitational waves. It was the smoking gun, the first indirect proof. But seeing the waves themselves, that was still out of reach. And the reason it was so hard is just the scale of the challenge. By the time these cosmic ripples get all the way to Earth, their effect is unbelievably small. As one scientist put it, it's like trying to measure a change in the distance to the nearest star that's only the width of a single human hair. How on earth do you even begin to measure that? Well, if you want to measure a tiny effect, you build something enormous. That's the whole idea behind LIGO. It's this giant L-shaped detector with two arms. each one a 4-kilometer-long vacuum tube. They shoot a laser, split it in two, send it down both arms, bounce it off mirrors, and bring it back together. Now, if nothing's happening, those two laser beams should perfectly cancel each other out when they recombine. But if a gravitational wave passes by, it stretches one arm and squeezes the other, just a tiny, tiny bit. That knocks the lasers out of sync and you get a flicker of light. And the change they detected from that black hole collision, it was just 1,000th the width of a single proton. That is an almost impossibly precise measurement. So you might be wondering, okay, that's incredible engineering, but why go through all that trouble? Why does this matter so much? Because this discovery wasn't just about proving Einstein right again. It was about fundamentally changing the way we see the universe. Think about it. For all of human history, everything we've known about the cosmos has come to us through light, through the electromagnetic spectrum. It's all we've ever had. Gravitational waves are completely different. They're not light. They're vibrations in the fabric of reality itself. It's like we've spent our entire existence watching a silent movie, and someone just walked in and finally turned on the sound. And this new sense is a total game changer. These waves travel through gas, dust, stars, pretty much anything, completely undisturbed. They let us listen in on things that are totally dark, like two black holes merging. They're a pristine messenger carrying an unfiltered story straight from their source. They could even let us hear the echo of the Big Bang itself, from a time before the universe even had light. That first detection back in 2015, that wasn't the end of the story. That was just the opening note. Since then, we've heard dozens more cosmic events, including the collision of neutron stars. We are right at the beginning of a whole new kind of astronomy. We've thrown open a new window to the cosmos. And the really exciting question is, what else is out there just waiting to be heard?